what is the limit of a function? So we have a graph over here of the function y equals to x minus 1. Okay, so I want to know what is happening to the y value when I'm getting closer and closer to a particular x value. So just for the sake of it, let's say that when we are getting closer and closer to the value of x equals to 1, what is happening to y? So we'll use the simple table of value to illustrate this. So since this is a graph, I can get closer and closer to x equals to 1 from two directions, from going from left to right and going from right to left. So in this side over here, in this part of the table of value, we are going from left to right. So when x is 0.5, which is a little far from x equals to 1, the y value is minus 0.5. When x is 0.9, a lot more closer to 1, y is minus 0.1. When x is 0.99, y is negative 0.01. When x is very close to 1, that is when x is 0.999, now y is negative 0.001. Okay, so that is from the left hand side. Now on the right hand side, meaning we're going from right to the left in this direction. When x is 1.5, y is going to be 0.5. When x is very close to 1, which is 1.1, y is going to be 0.1. When x is 1.005, which is like almost very close to 1, y is 0.005. So using this table of values and also looking at the graph, we can say that as x is getting closer and closer to 1, whether it's from the left hand side over here or whether it's from the right hand side over here, as x is getting closer and closer to 1, the y value is getting closer and closer to 0. We can say that, right? We don't know what is happening exactly when x is equal to 1. The y value may exist, the y value may not exist, it may be undefined. We know that as x tends to get closer and closer to 1 from either direction, the right hand side or the left hand side, the y value is getting closer and closer to 0, as we can see from the graph and also from this table of values. So this is basically, in very simple terms, what the limit of a function is. So the notation for limits is, we say that the limit as x approaches a particular number a of a function is equal to a value L. So in our example, we know that the limit as x approaches 1 of the function, which is x minus 1, is equal to what? So we know that as x tends to get closer and closer to 1, the y value is getting closer and closer to 0. So we can say that this is simply just 0. We do not know what is the y value when x equals to 1, and we also don't want to know what this value is when we're talking of limits. All we want to know is that when x is getting closer and closer to a certain number a, the y value is getting closer and closer to what? That is simply the idea of limits. Alright, so there's three main ways of finding limits. There is a numerical, graphical, and analytical approach. As you will see, the analytical approach is the most effective and the best way to do so. But let's talk about the numerical approach for now. So the numerical approach is simply what we just did in the previous example, right? So in this case, we're told to find the limit as x approaches 0 of the function x squared minus 1. So what this is saying is that when x is getting closer and closer to 0, what is y getting closer and closer to? So the simplest way, as we just did in the previous example, is to make table of values for both cases when x approaches 0 from the left hand side, meaning from left to right, and when x approaches 0 from the right hand side, meaning from right to left. So when x is minus 0.5, y is going to be minus 0.75. Now when x is a lot more closer to 0, let's say that when x is minus 0.05, the y value is minus 0.9975. When x is a lot more closer now to 0, let's say when x is 0.001, the y value is minus 0.9999, right? So this is from the left hand side, okay? Now similarly, as x approaches 0 from the right hand side, meaning that as x is getting closer and closer to 0 from the right hand side, so we can say that if when x is 0.5, the y value is minus 0.75. When x is a lot more closer to 0 now from the right hand side, so when x is positive 0.05, y is still going to be minus 0.9975. when x is 0.001, the y value is minus 0.9999. Alright, so just like how we did in the previous example, it's safe to assume that as x is getting closer and closer to 0, okay, the y value is getting closer and closer to minus 1, right? So therefore, we can say that the limit as x approaches 0 of x squared minus 1 is equal to minus 1. Again, I'm putting a little emphasis over here just so you get the idea of what we're doing. We are not finding out the y value when x is exactly 0. What we are saying is that when x is getting closer and closer to 0, the y value is getting closer and closer to minus 1. So that is the whole idea of the numerical approach. Alright, so the second approach for evaluating limits is the graphical approach. So we'll solve the same question as we solved previously. The limit as x approaches 0 of the function x squared minus 1. As the name suggests, in the graphical approach, we are supposed to plot a graph. So of course, this is going to be very tedious if you have to physically, plot the graph by hand. So how the graphical approach works is just making the use of the graph to see what value y approaches when x tends to get closer and closer to 0. This part over here says that as x approaches 0, which is the same thing as x tends to get closer and closer to 0. Okay, so let's look at the graph now. So we know that this is your x-axis and this is your y-axis. So when x is getting closer and closer to 0, right, when you're getting closer and closer to 0 in the graph from the right-hand side and from the left-hand side, the y value gets closer and closer to what? Pretty simple, right? The y value gets closer and closer to minus 1. So that is simply just how the graphical approach works. We actually also use the graphical approach in the first example. So we say that the limit as x approached 1 was equal to 0. So, we looked at the graph and you can see that as you approach x equals to 1 from the left-hand side over here, the y value is getting closer and closer to 0. And also when you approach x equals to 1 from the right-hand side over here, the y value was getting closer and closer to 0. So therefore, we said the limit was equal to 0. So that's more or less how the graphical approach works. It's easy to identify, but plotting the graph can be a tedious process. We're going to talk about a fundamental concept, that is the one-sided limits. So we're given a graph of the function y equals to x squared minus 1. So let's say that we want to find the limit as x approaches 1 of x squared minus 1. So how we did this using the graphical approach is that for the function, as x gets closer and closer to 1 from the right-hand side, y is getting closer and closer to what? Y is getting closer and closer to 0. And then we say that as x gets closer and closer to 1 from the left-hand side of the function, y is getting closer and closer to 0 again. Now, since when we move closer and closer to x equals to 1 from both the right-hand side and the left-hand side, y is still getting closer and closer to 0, then we can generalize this and say that the limit as x approaches 1 of the function x squared minus 1 is equal to 0. So this thing over here is what we call the right-hand side limit. Okay, so how we can write this is that the limit as x approaches 1 from the right, so we use the plus of the function x squared minus 1 is equal to 0. So why we use the plus over here is that when we are approaching x from the right hand side, so that means we are getting closer and closer to 1 from the right hand side, so in this direction. So our values are slightly, in the slightest terms, greater than 1, right? They are not equal to 1. They are like 1.000. You can think of that. You can think of it in that way, right? Similarly, what we did over here is what we call the left-hand limit. So the notation for that would be the limit as x approaches 1 from the left-hand side. So we use the minus sign of x squared minus 1 equals to 0. So why we use the minus sign again? It's intuitive, but what this means is that we are approaching x equals to 1 from the left-hand side, right? So this means that we are almost at 1, but we are not exactly at 1. So if we are approaching x equals to 1 from the left-hand side, so that means our value is slightly, in the slightest terms, lesser than 1. So that's why there is the minus sign. So we can use this concept of one-sided limits to come up with a very important definition. So we say that the limit as x approaches a of a given function, any given function, equals to some value L if and only if the one-sided limits also equal the same value L. So if and only if the limit as x approaches a from the right-hand side of f of x equals to the same value L, and the limit as x approaches a from the left-hand side of the function also equals to the same value L, right? So the definition sounds a little complex, but again, we'll make life simple using an example. Come back to the example that we just did. The limit as x approaches 1 from the right hand side over here is equal to 0. The limit as x approaches 1 from the left hand side equals to 0. The one-sided limits are equal to each other. So therefore, we can generalize this to the limit as x approaches 1. So therefore, we say that since the one-sided limits are equal, the overall limit as x approaches 1 is equal to 0. So that is the whole concept of one-sided limits. We will come across situations where the one-sided limits are not equal. So in that case, the individual one-sided limits are going to exist, but the overall limit will not exist. We'll discuss more about that as we move along the chapter. But for now, this is the whole concept of one-sided limits. So the important thing to remember is the overall limit as x approaches a is only going to exist if the one-sided limits, meaning the limit as x approaches a from the right, equals the limit as x approaches a from the left. So to better understand the idea of the one-sided limits, we'll look at one more example. So this is a piecewise function. So it tells you that when x is greater than or equal to 0, right, y is equal to 1. But when x is less than 0, y is equal to 0. So if we want to find the limit as x approaches 0 of the function, right, what we need to do is we need to find the one-sided limits, right? So we need to find the limit as x approaches 0 from the right and from the left. So let's do the right-hand side limit first. So the limit as x approaches 0 from the right-hand side of f of x is equal to what? So we know that since we're approaching 0 from the right-hand side, so x is getting closer and closer to 0. So it's a value that is almost 0, but slightly, in the slightest terms, greater than 0. So which part of the function are we going to be looking at? So we're looking at this part of the function at this point in time. So the limit as x approaches 0 from the right-hand side is simply equal to 1. The limit as x approaches 0 from the left-hand side of our function is equal to what? So in this case, we're approaching 0 from the left-hand side. So it means that we are almost at 0, but it's a number that is slightly, in the slightest terms, less than 0. So since it's less than 0, we are looking at this part of the function. So the limit as x approaches 0 from the left-hand side is going to be equal to 0. So we have our one-sided limits, right? So if we were just asked the limit as x approaches 0 from the right-hand side, that's all we need. If we are asked the limit as x approaches 0 from the left-hand side, that's what we need. But since in this case the one-sided limits not equal to each other, and we are asked the limit as x approaches 0, we can say that this limit does not exist. The one-sided limits individually exist, but the overall limit does not exist because the one-sided limits are not equal to each other. If both of these one-sided limits were equal to each other, then the overall limit as x approaches 0 would be the same value as the one-sided limits, what we just saw in this definition over here. Alright, so the third and final approach for evaluating limits is the analytical approach. So this basically talks about the limit laws and the direct substitution property. So there are several limit laws. The first one is the sum or difference law. So this basically tells us that the limit of a sum, as you can see over here, the limit of a sum is the sum of the limit. The same thing applies to the difference, right? The limit of a difference is the difference of the limits. That's why there's a plus or minus over here. The second law is the product law. So this basically tells us that the limit of a product is a product of the limits. So the limit of f of x multiplied by g of x is the same thing as the limit of f of x multiplied by the limit of g of x, provided x approaches the same number a in all the cases. The third law is the quotient law. So this tells us that the limit of a quotient is the quotient of the limits. So the limit of f of x over g of x is the same as the limit of f of x divided by the limit of g of x as they approach a certain number a. The fourth law is the constant multiple law. So this basically says that the limit of a constant c multiplied by a function is the same thing as the constant multiplied by the limit of the function. Okay, so to better illustrate the limit laws, let's look at a few examples. So assume there is a function f of x. Don't worry about what the function exactly is, but just assume that there is this function f of x such that when x is getting closer and closer to minus 2, when x is approaching minus 2, y is getting closer and closer to 1. There's a second function g of x such that when x is getting closer and closer to minus 2, the y value is getting closer and closer to minus 1. So using this data, let's try and solve these few questions. So to solve this first question, we're going to use the first law, which was the sum law. So the limit of a sum is basically the sum of the limits. So this is the same thing as the limit as x approaches -2 of f of x plus the limit as x approaches -2 of g of x. So we know that this is 1 plus -1. So this basically gives you 0. The second example is the limit as x approaches -2 of f of x multiplied by g of x. So we are going to use the product law. The limit of a product is the product of the limits. So this can be written as the limit as x approaches -2 of f of x multiplied by the limit as x approaches -2 of g of x. So that's just 1 multiplied by -1. So therefore it gives you -1. The third question is the limit as x approaches -2 of f of x divided by g of x. So this is the quotient law. So the limit of a quotient is the quotient of the limit. So we can rewrite this as the limit as x approaches -2 of f of x divided by the limit as x approaches -2 of g of x. So we know that this is 1 over -1. So therefore the final answer is -1. This fourth question is the limit as x approaches 2 of 2 multiplied by f of x multiplied by g of x. So over here, first we're going to use the product law and break this down. So this is the limit as x approaches -2 of 2 f of x multiplied by the limit as x approaches -2 of g of x. Now we know that this part over here is a 2f of x, so it's a constant multiplied by a function. So we're basically going to use the constant multiplier law. That is basically that the limit of a constant multiplied by a function is basically just the constant multiplied by the limit of the function. Right? So we can rewrite this as such. Okay, and this remains as it was, g of x. So we're going to get 2 multiplied by 1 multiplied by -1. So we're going to get -2. So now let's continue with the other limit laws. The fifth one is the power law. So when we have the limit as x approaches a number a, right, of f of x to the power n, so what we can do is we can take the whole limit and apply the power to it, right? Similarly, we can do the same when there is a root available. So we can take the root and apply it to the whole limit. In the seventh law, the limit as x approaches a particular number a of c, which is a constant, right, is just equal to the constant itself. So what this says is that when I say that the limit as x approaches a number a of c, so this means that the function y is just equal to c. So if y equals to a constant, right, the constant can be anything, right? Let's say the constant is 3. So the graph of y equals to 3 is just going to be this, right? Whatever the x value is, the y is just going to be equal to 3, right? So if x approaches, let's say 5, or if x approaches 10, or if x approaches -1, right, the y value is always going to be approaching 3, right? Because this is a constant. So that explains this limit law over here. The eighth one over here says that the limit as x approaches a number a of x is equal to the same number a. So again, this over here tells us that the function is y equals to x. So the graph of y equals to x is simply this, right? So the y value is simply whatever the x value is, right? So when x is 1, y is equal to 1. Okay, when x is, for example, 500, y is also going to be equal to 500. Okay, so in this case, when x approaches a particular number a, okay, the y value is going to be approaching the same number, right? So for example, when x approaches this 1 from right or left, the y value is also going to be approaching 1, right? Because the graph is y equal to x. So that explains this law. So the last two are special laws. So this says that as x approaches a of the function x to the power n, the limit is simply a to the power n. Similarly, the limit as x approaches a of x to the root n is equal to a to the root n. Okay, so these are special limits, and you kind of need to remember how they work. And now let's go ahead and solve some questions using these limit laws. So the limit as x approaches 2 of 3. So again, this basically tells us that the graph is just y equal to 3. So whatever number x approaches, the y value is just going to be approaching 3, right? So this is simply equal to 3. We use the law, the limit as x approaches a number a of c is just equal to the same constant c, right? The second one over here looks a little more complex. So the limit as x approaches 5 of 2x squared minus 3x plus 4. So first we are going to use the sum and the difference law to break it down. So this is the limit as x approaches 5 of 2x squared minus, so we're using difference law, limit as x approaches 5 of 3x plus the sum law, the limit as x approaches 5 of 4. So over here, we're going to use the constant multiple law. So we're just going to put 2 outside, multiplied by the limit as x approaches 5 of x squared, minus, we're going to put 3 outside, multiplied by the limit as x approaches 5 of x. And this part over here is simply what we did in this first example, right? So this is basically, you can say like a constant law. So we know that the graph is just going to be y equals to 4. So whatever value x approaches, y is just going to be approaching 4. So we can just write this as plus 4. Okay, so for this guy over here, we basically need to use the ninth law. So let's say that the limit as x approaches a of the function x to the power n is equal to a to the power n, right? So we are going to write this as 2 multiplied by, in this case, we know that the n is equal to 2. And what is a? So what number is x approaching? So x is approaching 5. So this is our a. So we can basically just evaluate this as a to the power n. So it becomes 5 to the power 2 minus 3 multiplied by the limit as x approaches 5 of x. So we know that this means that the function is y equal to x, right? So whatever the x value is, y is going to be the same value, right? So as x approaches 5, y is also going to approach 5. So this part we can evaluate it as 5 plus 4. So that just gives you 2 times 25 minus 15 plus 4, and hence this becomes 39. So therefore you can say that this is equal to 39. Okay, so let's look at this final example. Looks a little complex and we might have to use different sorts of laws. So first we can use the quotient law, right? So this is basically the limit as x approaches minus 2 of x cubed plus 2x squared minus 1 divided by the limit as x approaches minus 2 of 5 minus 3x. Now we can apply the sum difference law on both the numerator and the denominator. So we are opening up both the numerator and denominator. So this is the limit as x approaches minus 2 of x cubed plus the limit as x approaches minus 2 of 2x squared minus the limit as x approaches minus 2 of 1, everything divided by the limit as x approaches minus 2 of 5 minus the limit as x approaches minus 2 of 3x. Okay, now let's apply laws on every individual part. So the first one over here, so this is the limit as x approaches minus 2 of x cubed. So again, remember this law, we said that the limit as x approaches a number a of x to the power n is a to the power n. So to evaluate this, we know that a, the number that x approaches, is minus 2, and n, which is the power, is equal to 3. Right? So we solve the first part. The second part, we know that there is a constant over here, so we can put this constant outside for first. So this just becomes 2 multiplied by the limit as x approaches minus 2 of x squared. Right? The last part is just the limit as x approaches minus 2 of 1. So we know that in this case y is a constant, so y is just equal to 1. So whatever value x approaches, y is always going to approach 1. So in this case, this just becomes 1. Okay, this is in accordance to the law that said that the limit as x approaches a of a constant is equal to the constant itself. Divided by, the numerator is the same thing over here. The limit as x approaches minus 2 of 5, so that's just going to give you 5. Minus, there is a constant over here, so I will put the constant outside. 3 multiplied by the limit as x approaches minus 2 of x. Okay, so minus 2 cubed is minus 8 plus 2 multiplied by the limit of x squared. So over here we're going to have to use this law again. Okay, so we know that x approaches minus 2, so that's our a, and n, which is the power, is just 2. So we evaluated that part, then we have a minus 1 divided by 5 minus 3 times the limit as x approaches minus 2 of x. So the law said the limit as x approaches a number a of the function x, meaning that y equals to x is just equal to a. So in this case, this part over here is just going to evaluate to minus 2. So if we do the math over here, we get minus 8 minus 1 divided by 5 minus 6. So this basically is going to give us minus 1 divided by 11. So therefore, all of this evaluates to minus 1 over 11. So that's how we use the limit laws to evaluate limits. Okay, so now let's talk about the final part and the most important one, the direct substitution property. So this basically tells us that if the function f is either a polynomial or a rational function, and the value that x approaches, which is a, is within the domain of the function, then we can simply just plug in the value that x is approaching into the function to get the limit. So what this means is that, for example, in this case over here, we know that the function is equal to x minus 1. Now to find the limit, what we can simply do is just find the value of f of 1, right? So what is the y value when x equals 1, right? So since the function is x minus 1, I can just do the simple substitution, right? I can plug in the value of x. So I'm plugging in 1 minus 1 and that gives you 0. So this gives us 0. As we've seen, the direct substitution property basically makes our life simple, right? This is an example that we solved using the limit laws. But if we use the direct substitution property, all we need to do is to plug in the value as x approaches, right? To plug in this 5 everywhere we have an x. Okay, so this is just 2 multiplied by 5 squared minus 3 multiplied by 5 plus 4. That gives us 50 minus 15 plus 4, which is 39. And guess what? This is the same answer that we got using, I don't know, 3 or 4 different type of limit laws. So in this way, right, using the direct substitution property, it becomes much simpler to solve the limits, because what we have to do is just plug in the value that x is approaching, plug in this a value into the function, and that gives us the limit.